In this video, we're going to begin to cover one-dimensional motion. And so we will start with the basic definitions of quantities such as position, displacement, speed, velocity, and acceleration. The area of physics that we're covering is called kinematics. It's a subtopic of mechanics, which is everything related to motion. In kinematics, what we're doing is we're describing motion. So we're going to define those key terms that I just mentioned. We're also going to be starting with the simplest possible model. So one-dimensional motion, either horizontal or vertical. Objects don't have any size or shape. We treat them as basically points or particles. And we only allow for translational motion. So no rotation, just side to side or up and down motion. In order to get started, the first thing we have to be able to do is locate an object in space. And so the position of an object can be determined by just setting up a coordinate axis. And so here we have the x-axis. And if I've got a person here, I can say that their position is at 50 meters. Once we understand the concept of position, the next thing that we can do is specify distance. So let's say that our person, who starts out at a position of 50 meters, walks to 0 and then comes back and stops at 10 meters. What distance did they travel? Well, if we add up the fact that they went 50 meters all the way to 0 and then they came back 10 meters, the total distance they traveled would just be 50 meters plus 10 meters, or 60 meters. So distance is just how far did the object, in this case the person, travel. We're now going to define a term you might not be familiar with, which is displacement. Displacement of an object is defined in the following way. We use the term, or the symbol delta, to represent it. So delta x would be the displacement in the x direction, and it's defined as the final position minus the initial position. So first of all, delta, if you remember from math, delta means change. And so displacement is the final position. So 2 right now is representing final, and 1 is representing initial. So we get the final position minus the initial. You'll notice that if we calculate this for the example, our final position is 10, our initial position is 50. So 10 minus 50 is negative 40 meters. Notice that the displacement is very different from the distance that the object traveled. The other important thing to notice here is that distance is an example of what we call a scalar. Whereas displacement is an example of what we call a vector. And I'll talk more about that in just a second. When we look at the displacement, we can see that what the negative sign represents is that the object ended up to the left of where it started. So in a positive displacement, the object ends up to the right. In a negative displacement, the object ends up to the left of where the object started. Let's talk about what we mean by a vector versus a scalar. A scalar quantity is a quantity that can be completely described by just a number. So we say scalars have a magnitude, and magnitude just means a number. An example of a scalar is temperature. If you ask me what the temperature is today, I might say it's 18 degrees Celsius or 70 degrees Fahrenheit. There's no direction associated with temperature. It's just a number. Vectors, on the other hand, are quantities that have both a magnitude or number and a direction. Displacement is an example of a vector in that it's not only a number, but I want to know whether the displacement is to the right or to the left. So we need both a number and a direction to specify the displacement. We're going to see other examples of vectors include velocity, acceleration, and force. Since we're working only in one dimension right now, we can keep track of the vector nature of displacement by just understanding that a positive displacement means that it ended up to the right of where it started, and a negative displacement means that it ended up to the left. Once we get into two-dimensional motion, we'll have to be a little bit more sophisticated about this, but right now that's really what we need to remember. Let's define another quantity, one that you're probably pretty familiar with, which is average speed. Average speed is just the distance traveled divided by how much time it takes to travel that distance. So let's look at the example that we started with, where we had our person starting at the 50-meter position, traveling to 0, and then coming back to 10 meters. And let's say that they did this in an amount of time, delta t, equals 10 seconds. Well, we could then go ahead and calculate their average speed. The total distance that they traveled was 60 meters, and the amount of time it took them to do that was 10 seconds, and we see that the average speed would be 6 meters per second. To contrast with average speed, we now want to define a new quantity, which is average velocity. You'll notice that unlike average speed, which was a scalar, average velocity is a vector. We define the average velocity in terms of the displacement. So you'll notice that the average velocity is defined as the displacement per time interval. So again, assuming that we're studying the same motion, which took 10 seconds, and we have our person who started at the 50-meter line, went to 0 and came back to 10. If we look at what their average velocity was for this motion, you'll notice it's very different from the average speed. The displacement, again, is 10 minus 50. And now we're dividing by the time that took, which is 10 seconds. And we end up with an average velocity of -4 meters per second. That negative sign, again, is important because velocity is a vector. What this tells us is that we went in a direction to the left. So that's what that negative sign tells us. Notice also that the average velocity doesn't really tell us exactly what happened. It just says that if you start out at 50 meters and you want to end up at 10 meters in a time of 10 seconds, what you need to do is go at 4 meters per second to the left. That's really what it's telling us. Now that we've defined average velocity, we want to define something new called instantaneous velocity. The first thing that you want to understand about this is a weird concept, and it's an important concept. This, in fact, is where calculus comes from. So let's see why it's a weird concept. You'll notice that in our definition of average velocity, by necessity, it involves two times. It involves delta t, or t2 minus t1. So how does it even make sense to talk about a velocity at just one time? In other words, you think, well, that doesn't work because we can't divide by 0. We can't have a delta t of 0. So the way Isaac Newton figured out how to deal with this, and again, really why Isaac Newton had to invent calculus as he was doing physics, is he had to define instantaneous velocity as a limit. We define it as the limit as delta t goes to 0 of the average velocity. So it never gets to 0, but we get arbitrarily close to 0. And that's the whole idea. You'll notice that if we look at average velocity, since it's delta x over delta t, the average velocity between 2 points on a position versus time graph, you'll notice, is just the slope of the line between the 2 points. And you might remember in math we call that a secant line. So we can see that delta x over delta t is the definition of average velocity. Well, let's say that what we really wanted to know is what is the velocity at that point? Well, we might not be able to get exactly the velocity at that point, but we could get closer and closer to it if we brought these 2 points closer. What if instead of having my second point here, I brought it right to here? Well, now we'd be figuring out the slope of that line. And what if I brought it even closer? Then we'd be pretty close to finding the actual slope of the curve at that point, and that is the instantaneous velocity. So that's our definition. It's the limit of the average velocity as delta t goes to 0. Never quite gets there, but it gets arbitrarily close. So here's the important thing that we've just learned. The instantaneous velocity, which we're going to always denote just by the letter v, notice no bar over it anymore. The bar meant average. The instantaneous velocity is equal to the slope of the tangent to the curve at any point. So for example, if I wanted to know what is the velocity at time t1, what I would need to do is figure out what is the slope of the tangent to the graph at that point. That is the instantaneous velocity. You'll notice that as soon as we understand this, we can look at a graph of position versus time and understand how the object is moving. So you'll notice here at t equals 0, the object was moving pretty fast because we had a pretty large slope of x versus t. You'll notice that right in here, the object was moving pretty slowly because the slope of the graph was quite low. And again, by the time the object is here, the slope of the x versus t graph is quite high, and so the velocity is higher again. So that's a really, really important point, that the instantaneous velocity is equal to the slope of the tangent to the curve of our position versus time graph. Now, this has a fundamental relationship with calculus because it turns out that this is the definition of the derivative of x with respect to t. Now, many of you probably have not seen this yet. If you're first in Calculus 1, you probably haven't gotten here yet, and that's okay. I'm just going to give you a brief introduction, and then you'll learn more about this in calculus. dx dt both dx and dt are called infinitesimals, and again they represent very small or vanishingly small quantities. And the idea is that dx dt is simply a shorthand notation for this. So whenever you see dx dt, know that it simply represents the limit as delta t goes to 0 of the average velocity. So in a shorthand way, we can write the instantaneous velocity is the derivative of position with respect to time. And most importantly, we've learned that the derivative of a function gives the slope of the tangent to the function at any point. Remember, that's what we were just talking about on the last slide, that if I have a position versus time graph, if I look at the slope of any point along that graph, that is the instantaneous velocity. Let's talk about the different notation used in a calculus-based physics course versus a math course. This is really confusing when you're first taking both calculus and physics. In math, we usually plot y versus x, and we say that y is equal to f of x. And in this particular case, let's say that f of x is x squared plus 2, which you'll notice represents the graph below. Okay, so in physics, right now, what we're looking at is position as a function of time. So we're plotting x versus t. Usually in physics, we don't use the notation x of t like we do in math. usually when we write it in physics, we just write x equals t squared plus 2. So, because we're plotting x versus t, the derivative of this function, which is the instantaneous velocity, would be dx dt. Because remember, fundamentally the derivative is just related to the slope. So it's rise over run, or change in this value versus change in this value. When you learn about the derivative in math, though, the way you're going to write it is dy dx, simply because now y is the vertical axis and x is the horizontal axis. And x is your independent variable, whereas in physics, t is our independent variable. So just be aware of that obviously it's the same stuff we're talking about, but the notation can sometimes be confusing. Once we've defined velocity, the next thing we want to define is average acceleration. So again, the bar over a quantity means average, and average acceleration is how the velocity is changing per time. So you'll notice it's delta v over delta t, the change in velocity per time interval. One of the things that you'll notice about this is that we can define a unit for acceleration. Now, if you've had physics before, like in high school, you probably know the answer already, but let's go through it. You'll notice that velocity has units of meters per second, time has units of seconds, so the unit of acceleration is meters per second per second. Now, it turns out there's a shorthand way we can write that. If we write meters per second divided by seconds, and now we do some fraction work here, we could rewrite that as meters per second divided by seconds over 1, or meters per second times 1 over seconds. You'll notice that we get meters per second squared. So usually when we write acceleration, we use the units meters per second squared. But I want you to always remember that that's simply a shorthand for this, because that's where the meaning is. Meters per second per second. So let's see how that gives us meaning. If I tell you that the acceleration is 5 meters per second, and I tell you that at time t equals 0, the velocity of our object is 10 meters per second. How fast would the object be going after 1 second? Well, the answer is it would be going 15 meters per second, because what this is telling you is that for every second that goes by, the velocity is changing by 5 meters per second. So 5 meters per second means the velocity changes 5 meters per second for every second that goes by. So then after another second, we'd be going to 20 meters per second, because once again, it would have changed by 5 meters per second in that second. So if you can remember that this is really what the units are of acceleration, that's going to help you remember what acceleration means. It means the velocity is changing, and it tells you how much it's changing per second. Now, just like we defined instantaneous velocity, we can do the same thing for acceleration. We're going to do it the exact same way. Instantaneous acceleration is defined as the limit of the average acceleration. Okay, so it's the limit of the average acceleration, delta v over delta t, as delta t goes to 0. And again, this can be related to the calculus concept of a derivative. The instantaneous acceleration is the derivative of the velocity versus time. Remember that this is simply a shorthand notation for this. Now, most importantly for us right now, what we want to understand is that when we say acceleration is the derivative of velocity versus time, what that's telling us is if I plot velocity versus time, then the slope of the graph at any point is the acceleration. You'll notice for this particular velocity versus time graph I have, you'll notice that the slope isn't changing. So just by looking at this graph, we know that the acceleration is positive because it's a positive slope. And we can also see that the acceleration is constant. I'm just going to note here that we can also write acceleration as the second derivative of position versus time. I'm not going to use this notation anymore until you've seen it in calculus, but this is simply the shorthand way of saying take the derivative twice. So we've said that velocity is the derivative of position versus time. So if we take the derivative again, we can write it either this way or this way, the second derivative of the position as a function of time. Let's look at one last example, and that is throwing an object up in the air. So let's say that we throw our object up, we give it some initial velocity straight up, and let's look at what the height of the object looks like as a function of time. So now instead of using x, I'm using y, simply because it's a vertical motion. Well, assuming that we throw our ball starting at what we're going to call y is equal to 0, what we would find is that the position as a function of time graph would look something like this. It looks like a parabola. In other words, we cover more distance early on, and then we get to a point where we reach the highest point of the motion, and then the motion reverses and the object comes back down. Okay, so picture yourself just throwing a ball up into the air. Well, here's what we've learned. We've learned that the instantaneous velocity is the derivative of position versus time. In this case, I'll write that as dy dt, since we're using y instead of x for the vertical direction. And most importantly, what we know is what that means is to find v at any time, we'll use the slope of the position versus time graph. So let's look at the slope right here at t equals 0. Notice that our slope is as big as it's ever going to get. Therefore, when we plot y versus t, we can see that our initial velocity is high. At some point here, we notice that the velocity is less, so maybe right there. Notice the slope of position versus time at the top is 0. So it's going to go through 0. And then we could do the same thing looking at what the velocity is at that point, and then finally right at the end we can see it's a negative maximum. And you can see that what I get is a negative straight line. So that's our final velocity and our initial velocity. And most importantly, the velocity is 0 when the object is at its highest point. Now we also have learned that the slope of the velocity versus time graph at any time gives us the instantaneous acceleration. Notice that the slope of this graph is negative, and it's also constant. It doesn't change. So our acceleration versus time graph would look like this. It's at some constant negative value. For those of you who have had physics before, you know what that value is. That's what we call the acceleration due to gravity, or negative 9.8 meters per second squared. One of the things that I want you to notice is at the top of the motion, where the object is at its highest point, the velocity is 0. However, the acceleration is not 0. That's something that often is hard for students to understand. But remember, the acceleration is how the velocity is changing. So just because momentarily the velocity is 0, it doesn't mean that it's not changing, because an instant before it was positive, an instant later it's negative. So the velocity is still changing even as it goes through 0. Therefore, the acceleration is not 0. If the acceleration were 0 at the top, the object would never fall back down, because a velocity of 0 and an acceleration of 0 would mean the object no longer can move.